OS task scheduling, network rate limiting, and Dijkstra shortest paths all need the same thing, a priority queue. It must keep accepting new elements while always being able to pop the highest priority one. The binary heap achieves this with a surprisingly simple idea. One option keeps the array fully sorted. Popping the most urgent task is instant, but every insert has to find a slot and shift elements, which is big O of n. The other option keeps the array unsorted. Inserting is fast, but each pop must scan everything, so it is big O of n again. The key insight: we only ever care about the smallest element, so the full order of the rest is wasted work. Put the tasks in a complete binary tree, filled top to bottom and left to right with no gaps. Each number is minutes until the deadline, so smaller means more urgent. The only rule is the heap property. Every node is no larger than both of its children. Siblings are unconstrained. 10 and May 7th sit in either order. That purely local rule propagates upward and guarantees the global minimum sits at the root, readable in one glance. This is the earlier insight made concrete. A heap maintains order only between parent and child, which is far cheaper than sorting everything. Because the tree is complete, there are no gaps, so no pointers are needed. Just write the nodes into an array in level order. The node at index I has its left child at 2i plus 1, and its right child at 2i plus 2. Node 5 at index 1, Hector children at indices 3 and 4. Conversely, the parent of index I is floor of I minus 1 divided by 2. Moving up and down is pure arithmetic, which saves memory and stays cache-friendly. A new task arrives due in 4 minutes. First, append it at the end of the array, the next free slot of the complete tree, index 7. The shape stays a complete binary tree. But the heap property is violated. 4 is smaller than its parent 10. So swap the two. This step is called sifting up. Compare with the new parent. 4 is still smaller than 5. So swap once more. This time, 4 is greater than the root value 3, so nothing is violated, and the sift-up stops. It walked at most one leaf to root path, so it is big O of log n. Now pop the most urgent task from the heap we just built, the root value 3. Removing the root leaves a hole. Move the array's last element, 10, into the root and drop the tail, keeping the tree complete. 10 is clearly too large. Swap it with the smaller of its two children, which is 4. Picking the smaller child matters, otherwise the promoted node would still exceed its sibling. Keep going down. The children of 10 are 5 and 7, so swap with the smaller one, 5. This step is called sifting down. 10 has reached a leaf with no children left to compare, so the sift down ends. The new top is 4, and again only one root to leaf path was walked, big O of log n. A binary heap is a complete binary tree that only requires each node to be no larger than its children, and it lives directly in an array with no pointers. Peaking the minimum is big O of 1. Insert and extract are both big O of log n. Given all n elements at once, bottom-up heapify builds the heap in big O of n. Its limits. Searching for an arbitrary element is slow, and merging two heaps is not efficient. When merging matters, a pairing or Fibonacci heap is used instead.